Till now, what we discussed, Boolean algebra number system. We need to continue some more time with the Boolean algebra. In the earlier discussion of the Boolean algebra, we were discuss the various operators, derived operators, and the relations among the various operators, etc. Here, the next topic what we are starting, if you look to the first class notes, after covering the number system, I said we'll be starting the K-map. So let us start now the K-map. The Boolean algebra work and K-map work all together basically for reading the minimal expressions. Ultimately, our interest is to read the minimal expressions, either maybe with the Boolean algebra procedure or maybe with the K-map. But when we are trying to read the minimal expressions or simplified expressions using the Boolean algebra properties, there are certain limitations. We need to identify first what are the limitations we are having to read the minimal expressions using Boolean algebra properties. We need to understand what difficulties we are having to read the minimal expressions using the Boolean algebra properties. Once we are understanding the difficulties, later we'll think for a systematic procedure. The systematic procedure is, on the systematic procedure, we'll be talking as this K-map. So let me discuss first what difficulties we are having to read the simplified expressions using the Boolean algebra properties. To understand this, let us work out a question. Simplify the given Boolean function. Simplify the given Boolean function using Boolean algebra properties. Using the Boolean algebra properties, where the given Boolean function f of xyz is equal to 0, 2, 3, 4, 5 and 7. Where the function f of xyz is equal to the minterms 0, 2, 3, 4, 5 and 7. So the function, it is available in the compact canonical SOP form. To simplify the function using properties, we need to read the function in the expanded canonical SOP form. If you write the expanded canonical SOP form for this function, couple of times we did this sort of work while working few problems in the chapter 2 Boolean algebra or a few other questions which are on our own we did on the class. So if you look here, the expanded canonical form for minterm 0, the product form in terms of the variables must be x complement, y complement, z complement, and so on. Like this, we must read the other products. So x complement y, z complement x, y complement, z complement, x complement y, z, minterm 3, next minterm 4, x, y complement, z complement, next product x, y complement, z, the last product x, y, z. So this is the expanded canonical SOP form for the function which is given in the compact canonical SOP form. Using properties, when we are trying to do the simplification, our interest is to simplify the given Boolean function using Boolean algebra properties. So to simplify this function using Boolean algebra properties, the work what we are having is effectively we will be grouping the terms. While grouping the terms, we are eliminating the variables. It is the work what we are having to simplify the function using properties. If you look to this equation 1, we are having here possibility to group the terms in many different ways. We are having possibility to group the terms in many different ways. One of the possible way, let us group here and let us look to the simplification. we are having possibility to group the first two terms. We are grouping the first two terms. From the grouping of the first two terms, the product what we are looking is X complement, Z complement. Because from the first two product terms, we are recognizing X complement, Z complement is common. Then within the parenthesis, it is Y complement or with Y. When it is Y complement or with Y, using Boolean algebra fourth property, it is 1. And using the Boolean algebra second property, 1 and with anything is anything is X complement, Z complement. So like this, if you look here, we are having possibility to group this second, third. So while grouping second, third, the product will be X complement Y. We are having possibility to group this fourth and fifth. We are having possibility to group this fifth and sixth. So while grouping fourth and fifth, we are having this is X, Y complement. From the last two products, it is XZ. This let us name as equation 2. We are looking this equation 2 is having lesser number of terms comparing the equation 1. Once this equation is with lesser number of terms comparing the equation 1, then definitely we need to speak it is one of the possible simplified form for the given function f. It is one of the possible simplified form for the given function f. Now let's take a small question on this equation 2. Try to simplify this equation 2. If any further simplification is possible, try to simplify this equation 2 while grouping the terms. Now don't look to the equation 1. Don't look to the equation 1. Just referring to the equation 2, if at all any further simplification is possible, try to simplify this equation 2. So you pause the video and try. If you try to simplify this equation 2, your answer is supposed to be further simplification is not possible on this equation 2. Further simplification is not possible on this equation 2. Once further simplification is not possible on this equation 2, we are naming such equation as irredundant expression or irreducible expression. The expression which is not possible to simplify any more further, such expression we are naming as irredundant expression or irreducible expression. So better note down the expression which is not possible to simplify any more further. The expression which is not possible to simplify any more further is called an irredundant expression, is called an irredundant expression or irreducible expression. Is called an irredundant expression or irreducible expression. Hence, we are naming now this equation 2 as an irredundant expression or irreducible expression. I was talking while giving this equation, I was mentioning we are having possibility to group the terms many different ways. Suppose if we remodify this grouping of the terms, if we remodify the grouping of the terms like this, let us group first two terms. Let us group the first term, the fourth term. Let us group third term, the last term, and let us group the last two terms. The grouping may be of anything. With any possible grouping, our interest is to cover every min term. The grouping may be of anything. With any possible grouping, our interest is to cover every min term. So we are looking with this grouping also, we are having coverage of every min term. With this grouping also, we are looking to the coverage of every min term. Once we are having coverage of every min term with this grouping, then let's try to look the simplified expression. From the first two terms, it is x complement, z complement. From the first and fourth term, it is y complement, z complement. From the third and last term, it is yz. From the last two terms, it is xz. So, this equation 3 also having lesser number of terms comparing the equation 1. While looking to this equation 3 with lesser number of terms comparing the equation 1, definitely we are accepting it is also one of the possibly simplified expression for the given Boolean function f. It is also one possible Boolean expression for the given Boolean function f. As similar to this equation 2, let us think on this equation 3. If you try any further simplification on this equation 3, any further simplification is it possible on this equation 3? Let us try. If you try, definitely you will be answering further simplification is not possible on this equation 3 also. Once further simplification is not possible on this equation 3, we must speak even this equation 3 also as an irredundant expression or irreducible expression. The equation 3 also we must name as an irredundant expression or irreducible expression. Suppose if we remodify this grouping further like this, let us group the first two terms. We are doing this problem some specific purpose. We are doing this problem, as I said, some specific purpose. The specific purpose what I mentioned was what difficulties we are having to read the simplified expressions using Boolean algebra properties. To understand that, we are doing this. So let us group the first two terms. Let us group third and last term, and let us group this fourth and fifth term. And we are looking with this grouping also, we are having coverage of every min term. Once we are having coverage of every min term with this grouping, then the simplified expression we are reading as from the first two terms x complement, z complement. From the third and last term it is yz. From the fourth and fifth term it is x y bar. So we are looking this equation 4 also having lesser number of terms comparing the equation 1. Once the equation 4 is having lesser number of terms comparing the equation 1, definitely we are speaking the equation 4 is one of the simplified expression for the given function f. Equation 4 is one of the simplified expression for the given function f. As similar to the equation 2 and 3, if we try to simplify this equation 4 any more further simplification is not possible even on this equation 4. Once further simplification is not possible on this equation 4, definitely we are speaking this equation 4 also as an irredundant expression or irreducible expression. We must speak the equation 4 also as an irredundant expression or irreducible expression. So basically, with all this work, what is our need? So what is our requirement? What is ultimate aim with all this work? Ultimately, with all this work, our requirement, our aim is reducing the cost of the digital circuit. The cost of the digital circuit will be less as and when the expression contains lesser number of terms. While discussing the consensus property, we had a little discussion about the cost of the logic circuit. If you are remembering well, without any difficulty, you can accept the statement what I was mentioning. Ultimately, our requirement with all this work is minimizing hardware cost of the digital system or digital circuit. Any digital system or any digital circuit cost will be less as and when for realizing the digital system or the digital circuit, the expression or expressions what we are using, those expressions are expressions as and when they are with lesser number of terms, default the cost of the logic circuit will be less. So knowing this knowledge, if somebody is asking us to realize the function f. Somebody is asking us to realize this function f. With all this work, what we did till now, based on this work, definitely for realizing this logic circuit, we are preferring to use the equation 4. We are not using this equation 2 or this equation 3. The reason is very simple. The equation 2 or the equation 3 are with 4 terms, whereas the equation 4 with only 3 terms. The expression which is having lesser number of terms, definitely it is using lesser number of logic gates. If you use this 2 or if you use this 3, we are having 4 products, so 4 AND gates. Whereas here 3 products, so 3 AND gates. So cost straightforward less. Number of gates are less. And here we need, either maybe for equation 2 or 3, we need the OR gate with 4 inputs because of the 4 product terms. It is basically 2-level circuit as we discussed earlier. So we need at level 2 a OR gate with 4 inputs, whereas here we need a OR gate with 3 inputs. We know, we discussed, we learned, as and when the fan-in of a logic gate is less, that the number of inputs of logic gates is less, the cost of the logic circuit is less. Hence, when we are looking to the implementation of this function, definitely based on the work what we did till now, we prefer to use the equation 4. We are not using this equation 2 or this equation 3. And of course, with any remodified grouping on this equation 1, any expression is possible even with lesser than 3 terms. With any remodified grouping on this equation 1, if any expression is possible with lesser than 3 terms, then definitely we are not using this equation 4 also. We will be using that equation which is resulting with lesser than 3 terms. But of course, on this given function, if we try in any possible way, we can't read any expression with not less than 3 terms. We can't read any expression with not less than 3 terms. Listen my statement well. I am speaking, we can't read any expression with not less than 3 terms. But I am not talking, this is the only one form with the 3 terms that I am not talking. My statement is, you can't read any expression with not less than 3 terms. But I am not talking, it is the only one expression with 3 terms that I am not talking. Okay. So, if you accept my statement, then we are looking for realizing this function, we need an expression which is with minimum 3 terms. The equation 2, the equation 3, the equation 4 all are irredundant expressions. But as far as the realization of the function is concerned, the equation 4 is having a speciality over the equation 2 or 3. So based on this, the irredundant expression 4 must be given a new name. As for the realization of the function is concerned, we are using equation 4. Hence, as far as the realization of the function is concerned, we must name this equation 4 or irredundant expression 4 with a new name. The new name what we are giving for this equation 4 is minimal expression. We are giving a new name for this is minimal expression. So it's a new word we are come across, so we need to define this word. So note down. Minimal expression is the expression. Minimal expression is the expression. It must contain minimum number of terms. Minimal expression is the expression. It must contain minimum number of terms. And each term with minimum number of literals. And each term with a minimum number of literals. And each term with a minimum number of literals. Minimal expression is the expression. It must contain minimum number of terms. And each term with a minimum number of literals. So, the statement what you noted, you are recognizing in the definition of the minimal expression, there are 2 conditions. there are two conditions. One condition is the number of terms in the expression must be minimum. Other condition is each product with minimum number of literals. Each product with minimum number of literals. We already know what advantage we are having when the expression contains the minimum number of terms. When the expression contains the minimum number of terms, if at all our discussion is limited to only on the SOP form, then definitely IND gates are coming to be less. As I said, our discussion, if at all we are limiting to only on the SOP, once the terms are less, the number of IND gates are less, because here for realizing these or this you need 4 IND gates, whereas here we need only 3 gates. And whenever each product is with lesser number of literals, whenever the product is with lesser number of literals, then the fan-in for the logic gate is less. As we already learned, as and when the fan-in is less, the cost of the logic gate is less. The whole. Once the expression is in the minimal form, using this minimal expression when we are realizing circuit, we are guarantee, without any second thought, we are guarantee the cost of the logic circuit will be less. Hence, for realizing digital circuits, we must use only minimal expressions. Hence, for realizing digital circuits, we must use only the minimal expressions. Better make a note. For realizing digital circuits, we must use only the minimal expressions. So, you need to highlight in your notes. So, you need to highlight the statement, what we mentioned with a highlight with a box or something. While watching videos, if you are not getting enough time to note down, you pause the video and note down. You pause the video and you can note down. And somewhere if at all you are looking, the video or our discussion is going slow, if at all you feel you are having a facility to fast the video. So as for your convenient, you try to use the facility. If at all you are making a note, if time not permitting to note, pause the video and note. If something you are little familiar and you don't want to spend time much on that, you can make it as a fast. So as for your convenient, you can try. But here, as a class of audience consisting of all different type of students, all caliber students, so our work will be to make the understanding of every student. Okay, somebody is familiar may feel sometimes slow, but it is not the case. So we have to take care for every student. Those who are just say college passed out or very fresh or not familiar with the subject, they need to cope up. Such students also need to cope up. So taking consideration of all such students as a class audience in general. So we are having this sort of recording. Okay, back to this question. Just look this equation 1. Try to think with any remodified grouping. Any expression is possible with 3 terms other than this 4. With any remodified grouping, just try to think any expression is it possible with 3 terms other than this 4. If you try well, your answer is yes. We are having possibility with remodified grouping on this equation 1. Other expression also possible, which will be as similar to this equation 4 with only 3 terms. It is possible. Just look how, or while grouping which terms it is possible, just think. If you look here well, we are having possibility while grouping the first and 4, while grouping second and third, while grouping last 2 terms. So we are looking with this grouping also we are having coverage of every min-term. So while having coverage of every min-term with this grouping, then the expression From the second and third term, we are having it is x complement y. From the first and fourth term, it is y complement z complement. From the last two terms, it is xz. That is named, it is equation 5. The equation 5 also having lesser number of terms comparing the equation 1. While having the equation 5 with lesser number of terms comparing the equation 1, definitely we are speaking it is one of the possible simplified expression. And if you try to simplify this equation 5 any more further, as similar to the equation 2, 3, 4, any further simplification is not possible on this equation 5. If you try to simplify this equation 5 as similar to the equation 2, 3, 4, further simplification is not possible on this equation 5. Once further simplification is not possible on this equation 5, then definitely we are speaking it is also one possible irredent expression or irreducible expression. One possible irredent expression or irreducible expression. An irredent expression or irreducible expression with the three terms. The irredent expression or irreducible expression with the three terms, we already accepted this as a minimal expression. So based on this, we must accept even this equation 5 also as an minimal expression. Hence, we must accept this equation 5 also as an minimal expression. So while looking to this example, you can speak a few conclusions. We are having few observations. Those observations, they are speaking as few conclusions. Just try to identify what observations we are having from this work. What observations we are having from this work, try to identify. So one observation is, better note down, the given function may be having more than one form of an irredent expression. The given function may be having more than one form of an irredent expression. The given function may be having more than one form of an irredent expression. Next point. All irredent expressions may not be minimal. All irredent expressions may not be minimal. Next point. Minimal expression may not be unique. Minimal expression may not be unique. Minimal expression may not be unique. So these are the observations what we are having while looking to the example what we discussed till now. ये observations अपन बता सकते, ये example what we discussed till now, ये example के हिसाब से ये observations we are having, these are the observations. First point क्या है? The given Boolean function may be having more than one form of an irredent expression. That is observation what we are having. A equation 2, 3, 4, 5 पूरा irredent expression है. Same function equation 1 के ऊपर. Hence, the given function we are speaking may be having more than one form of an irredent expression. Second observation क्या है? All irredent expressions may not be minimal. That is the thing what we are having. ये तो सही है. The equation 2, 3 both irredent expressions है, मगर ये तो minimal expressions नहीं है. So that every irredent expression may not be minimal, but reverse, opposite में तो true है. Every minimal expression must be an irredent expression. Every minimal expression must be an irredent expression. But every irredent expression may not be guaranteed to be minimal expression. Third point, we mentioned, third point अपन क्या बताया? Minimal expression may not be unique. ये तो है. The equation 4, 5 देखे तो both are minimal expressions. So that minimal expression may not be only single form. There is a possibility the minimal expression may be more than one form. So minimal expression may not be unique, may not be single form. So these are the observations what we are having while looking to the work what we are having now here. Now, just let us take the question. I mentioned somewhere in between while discussing this or earlier also, but let us try to consolidate. What advantages we are having to realize the functions by using the minimal expressions? Using minimal expressions, what advantages we are having, if at all, if you look using minimal expressions, the advantages, if you talk, the first thing what we can speak is the number of logic gates are less. First thing what we are looking is number of logic gates will be less. So we know in this example, if we are using the equation 2 or this equation 3, we are in need of 4 gates. I explained already. Whereas we use a 4 or 5, we are in need of only 3. So straightforward, number of logic gates are less. And other point, fan in for each logic gate is less. Fan in for each logic gate is less. So the minimal expression definition itself, it is giving a meaning. First condition is expression must contain minimum number of terms. Second condition is each product must be with a minimum number of literals. As and when the products are with a minimum number of literals, default the fan in for that AND gate will be less. Fan in will be less. And you can see further. Further, what we are looking is the power consumption is less. It's one of the important point. Power consumption will be less. While designing any digital system, the power consumption is one of the critical parameter, very important. So whenever you are purchasing a mobile phone, you need to bother what is the battery backup of that mobile phone. Whether the battery what we are having with that mobile phone is it giving power without any difficulty for 24 hours or 1 day or 2 days, etc. Sometimes we know when companies make to advertise as a marketing strategy, the backup for 48 hours, so and so hours, like that. So backup is for long period means the internal circuitry what we are having, that internal circuitry is consuming less power. Internal circuitry consuming less power, as engineer if at all you are talking, is nothing but the internal circuitry is drawing less current. Internal circuitry is drawing the less current. As and when the internal circuit is drawing the less current, naturally the aging of the battery will be more. Once aging of the battery is more means the backup will be for more hours or more days, so and so. So if you want to have current drawn from the supply, current drawn from the battery is to be less, then definitely the digital components what we are having inside the circuit will be less. It is required to be digital components to be less. In fact, we know in the definition of the minimal expression we are having one of the condition, the expression must contain minimum number of terms. Once the terms are less, the number of gates are less. So once we are having the lesser number of digital components, the current drawn from the supply, current drawn from the battery will be less. And also, if each device is having with lesser inputs, if each device is having a lesser input, then they are having less current, less connections with the battery. So less current will be drawn from the supply. So on the whole, once the expression is the minimal form, guarantee if you use that, the power consumption of the circuit will be less. As a cell phone example, what I said, mobile phone example, what I said. So battery backup will be long period. So power consumption will be need to be less. The next what we are looking is, we are having circuitry with less complexity. Circuit will be with less complexity. Lesser devices, smaller fan in, default the lesser connections will be having. Once the lesser connections we are having, complexity of circuit will be less. And with all these final conclusion you can speak, cost of the circuit will be less. Cost of the circuit will be less. So these are the advantages what we are having if we use the minimal expressions for realizing digital circuits. Whenever we are using the minimal expressions whenever we are using the minimal expression to realize the digital circuits, default advantages what we are having is number of logic gates are less, the fan-in for the logic gate is less, power consumption will be less, complexity of the circuit is less, the cost of the circuit will be less. These are the advantages what we are having to realize the digital circuit using the minimal expressions. Okay. So now if you look, our concern while giving this question was, what difficulties we are having to read the simplified expressions using properties. That question we took, and to understand that question, to speak answer on that question, we did this problem. So with this question, what we are understanding is, by using Boolean algebra properties, if at all we are trying to read the minimal expressions, first of all, there is no guarantee for us to read the minimal expressions. Somebody may be grouping with some procedure. So while grouping that, he or she may be getting this equation 2 or this equation 3. After reading this equation 2 or after reading this equation 3, further simplification is not possible. Once the further simplification is not possible, we are speaking, or we may be accepting the equation 2 itself or the equation 3 itself, we are speaking as a minimal expression. But of course, with all this understanding, we know the equation 2 or this equation 3 is not the minimal expression. It is not the 2 or 3, they are not the minimal expression. So it is a difficulty. We are not having guarantee to read the minimal expressions. Okay, by chance we are reading equation 4 or 5, it's well and good. Well and good. But even though I am talking as a larger digital circuit, as a larger design circuit, larger digital circuit, more components, larger digital circuit means more devices. So with the aspect to the larger digital circuit, if at all we are looking, it is better to read always all possible minimal expressions for the given Boolean function. It is better to read all possible minimal expressions for the given Boolean function. After reading this equation 4 or equation 5, we should not satisfy. We are supposed to try for all possible minimal expressions. Say for example, in this case, I will talk why it is better to know all possible minimal expressions. I will talk with a small example. Suppose consider one procedure, we group the terms of this equation 1 and you are having this equation 4, let us speak. After reading 4, when I ask any further simplification is possible or any other modified expression is possible with as a minimal expression, when I ask this as a question, and few of you might answer no further equation minimal expression is possible. A few of you may be getting, but I am talking in general. Few of you might be answered no further simplification, no further minimal expression is possible. No further equation we are having 3 terms. That might be your answer. Because it is a limitation as a human being for us. See, the work what we are having is effectively the work. If you look at the instant, what is the idea we are getting, based on that idea we are grouping the terms and we are doing the simplification. That is the difficulty basically here. Anyway, if at all we are reading this equation 4 and we are implementing the circuit by using equation 4. Consider, as I said already, consider an example we are having a larger digital system. In this larger digital system, we are having number of digital logic blocks. In the larger digital circuit, we are having the number of digital logic block. One of the digital logic block, let us assume as this function f. Consider this function f we are realizing by using, say, equation 4. Consider we are realizing the function f by using equation 4. At some other part of the digital circuit, somewhere here, we are having a need of a term, say for example xz. After realizing this block by using equation 4, wherever you need a product xz, to read the product xz, we need to use a separate AND gate. We need to use a separate AND gate to read the product xz. But consider, in the beginning itself, if you know equation 4 as well as equation 5, and knowing we are in need of the product xz, when I am asking to realize the given function f, then definitely instead of using 4, you prefer to use the equation 5. Because if you use the equation 5, wherever you are in need of a product xz, this product xz, we are tapping directly from the part of this function, from the part of this block. So that in that case, we are not in need of such extra AND gate. Like this, on the whole, we want to have the optimal cost. On the whole, if we want to have the optimal cost, then definitely we need to know all possible minimal expressions of the given Boolean function. On the whole, if we want to have the optimal cost, then definitely we need to know all possible minimal expressions. So, do you think what I said? It is better to know all possible minimal expressions for any any Boolean function. As again, I am repeating, after simplification, the given function to the equation 4 form, when I ask any other further simplification is possible as a minimal expression, that is with only 3 terms other than this 4, few of you might had answered no. But as I said already, with the Boolean algebra properties, if you try, these are the few problems we'll be having. So first of all, there is no guarantee for us to read the minimal form. Then if at all we are reading also, we may not be able to read all possible minimal expressions. Effectively work what we are having using properties for simplification is, we are grouping the terms and we are doing the simplification while eliminating the variables. So as a human being, we are having a limitation whether you or me or anybody else. Effective work is concerned, grouping the min terms and we are doing the simplification. That grouping, which terms you are grouping, that is just depending upon at that instant whatever the idea you are getting, based on the idea you are grouping. Sometimes we will be getting idea to group so and so terms to read this equation 5 or to read this equation 4, sometimes we may not be getting. That is a limitation as a human being. So based on all this, on the whole we are speaking, for reading the minimal expressions, if you try to use the Boolean algebra properties, definitely it is not the systematic procedure for reading the minimal expressions. For reading the minimal expressions, if we use the Boolean algebra properties, definitely it is not the systematic procedure for reading the minimal expressions. These are the limitations what we are having to read the minimal expressions using properties. The main purpose of doing this question is to understand few of these conceptual points. So such points are very, very important whenever you are appearing to an interview, maybe ISRO exam, maybe DRDO or any PSU, or sometimes even your GATE admission purpose. Generally, senior people will sit in the interviews and they will try to look your knowledge at a minute level. So when your knowledge they want to check at the minute level, definitely all these conceptual things are very, very important. Okay, so we concluded using properties. If at all we are trying to read the minimal expression, the difficulties we are having, we are not guaranteed to read sometimes the minimal expression, or we may not be having guaranteed to read all possible minimal expressions. To overcome these difficulties, we are having 2 standard systematic procedures. One procedure is Karnaugh map procedure, K-map procedure. One procedure is the K-map procedure, and other one is Quinn-McCluskey method. Other one is Quinn-McCluskey method. These are the two systematic procedures for reading the minimal expressions. This Quinn-McCluskey method, also named as tabulation method or tabulation procedure. The Quinn-McCluskey method also having the name as the tabulation procedure or tabulation method. Basically, these are the two systematic procedures for reading the minimal expressions. As far as our GATE question paper pattern is concerned, or in general any PSU written examination point of view, if you look, the questions are only objective type questions, multiple choice questions, numerical questions, basically objective type questions. Any question is not possible to frame as a numerical, as a objective type question with this Quinn-McCluskey method. With this Quinn-McCluskey method, question is not possible to frame as a objective type question. So that in our discussion, we are not discussing this Quinn-McCluskey method or tabulation procedure. We are not discussing. So in the class, we'll be discussing only this K-map. The class will be discussing only this K-map. Because the questions are possible to frame as objective type questions using the K-map procedure, not with this tabulation procedure. Few the small points we look among these two procedures. The K-map procedure, we are having possibility to use at the maximum up to 6 variables. The K-map procedure, we are having possibility to use at the maximum up to 6 variables. Beyond 6 variables, not possible to use the K-map procedure. It won't work out. The K-map procedure won't work out on the functions which are more than 6 variables. We can use at the maximum up to 6 variables. But coming to this Quinn-McCluskey method, there is no any such limitation. We are having possibility to use this procedure on function may be of any number of variables. And function may be any number of variables, maybe 3 variables, maybe 4 variables, or maybe 8 variables, maybe anything. Theoretically speaking, possible to use this procedure, second procedure, with on any number, on a function of any number of variables. Generally, in our practical usage, the K-map procedure we prefer to use most of the times up to 5 variables. Most of the times we prefer to use this up to 5 variables, but we can use up to 6 variables. And whenever functions are greater than or 5 variables, we prefer to use this Quinn-McCluskey method. Generally, that is the situation. Whenever the function is up to 5 variables, we prefer to use K-map. Behind 5 variable, we prefer to use the tabulation procedure or Quinn-McCluskey method. So now with all this knowledge, we can start learning of these K-maps. So the example what we discussed, based on this example, we identified K-map as one of the systematic procedure for reading the minimal expression. Let's discuss first the basics on the K-map. After learning the basics of the K-map, we will try to use the K-map for reading the minimal expressions. Let us start with the simple case of 2 variable. Suppose we are having a Boolean function on variables a and b. On variables a and b. For this 2 variable Boolean function, these are the 2 possible K-map formats. These are the 2 possible K-map format. In this format, the variable a we are taking as the row heading and b as the column heading. Whereas in this format, the variable a is column heading, the variable b is row heading. Based on the number of variables, we are having possibility of more than 1 K-map formats. The K-map formats may be of anything. Ultimately, on the given function, the results are not changing. Based on the K-map format, the results won't affect. The K-map format may be of anything. Ultimately, the results must be same. Whether we are looking to the number of prime implicants or essential prime implicants or the minimal expressions, irrespective of the K-map format, the results must be same. So anyway, if you look to this, here while taking the variable A as a row heading, for A we are having two possible values. One is Boolean constant 0, other is Boolean constant 1. So for this row, the A value, Boolean constant value is 0, for this row it is 1. Whereas here B is a column heading, B value for this column is 0, here it is 1. Similarly, coming to this format, A as column heading, A value for this column is 0, A value for this column is 1. B value for this row is 0, B value for this row is 1. Alternatively, also we can read here, having A is 1, we can speak here A and complementary form. So that here it must be complementary form. Similarly, having B value as 1 right side column, B must be uncomplementary form. Here B with 0, it must be complementary form. If we use the same notation even in this format, here possible to write as A. Now without writing anything here, without writing anything to the left side column, default possible for us to accept it must be A complement. Similarly here, it must be B, so default first row will be B complement. So wherever possible, try to cut down the writing work, so it will save some time for us. So like this also we can look. And based on this, in few of the textbooks you may be looking in detail work as something like this here, A complement, B complement, next here A complement B, next here A B complement, next here it is AB, something like this you may be reading sometimes. So going to such an extended work is not required. The minimum things what I mentioned, maybe the binary zeros are the Boolean constant, the Boolean variable 0 and 1, or with the Boolean variable names, it is enough to use this map. Okay, basically, if you see, the K-map is the alternative way of writing truth table. Basically, the K-map is the alternative way of writing truth table. Suppose we are having a function on n Boolean variables. For that function, whenever we are developing the truth table, we are having the truth table total to the power of n number of rows or to the power of n number of combinations, to the power of n number of rows or to the power of n number of combinations. The statement what I mentioned is the K-map is the alternative way of writing truth table. Based on this statement, even coming to this K-map, the similar thing we need to look. The K-map for a function of n variables, we are reading to the power of n number of cells. The K-map for a function of n variables, we are having to the power of n number of cells. Okay, so that if at all we are having a function on two variables, we are having the truth table with 4 rows. The same function, if at all we are looking as a K-map, we need to have 4 cells. So based on this, a cell supposed to be equivalent to row. When you compare the K-map with the truth table, a cell supposed to be equivalent to a row, or a row is supposed to be equivalent to cell whenever we are looking at coordination or one-to-one correlation between the truth table and K-map. And if you look at this, for this two variable case what we started, whatever the small squares we are reading here, these small squares we are naming as cells. What is the small squares we are reading here? These small squares are basically named as cells. When we are developing a truth table, say for example, in a function of 3 variables we are developing a truth table. Our normal practice, they are listing like this the possible combinations on these variables. We are listing the possible combinations like this on these variables. And left side of each row, we prefer to write its equivalent decimal number. Left side of each row, we prefer to write its equivalent decimal number. It's a normal practice for us most of the times. So similar work we need to extend. Similar work we need to extend even in the K-map. Here, these row numbers in the truth table, they are naming as row numbers. In the truth table, these decimal values, what we mentioned, they are naming as row numbers. Hence, in the K-map, these combinations supposed to be cell numbers. Supposed to be cell numbers. Instead of word row number, we suppose use a word as cell number. So if you look here, what are the cell numbers? What are the cell numbers? For reading cell numbers, basically we must read the binary variable values in order MSB to LSB. Some time back while discussing a question, I already mentioned, in general, whenever we are writing a function f on variable, say xn minus 1, xn minus 2 and so on, x1, x0, default, after function f, whatever the variable we are having as a first variable, it is the most significant bit variable and so on. The last variable is the least significant bit variable. So the order of the variable from the left to right we are having MSB to LSB. It is standard notation. It is a standard notation whenever we are dealing with Boolean function, maybe any number of variables. After writing f, after writing function f, what is the variable we are having? The first variable, that is a MSB and so on. The rightmost is a LSB variable. The notation what I use here, based on this, A must be MSB, B must be LSB. Based on this, if you look here, what is the cell number here? The cell number here we are reading as, if you try well, the cell number must be 1. Whereas here, the cell number, if you try well, it is 2. Why it is so? If you look, locationally, these two are at same place, but the cell numbers are differ. Why it is so? If you want to speak, we are having for this cell, A value is 0 and B value is 1. The equivalent decimal number is 1. So cell number is 1. Coming to this, here we are having A value is 1, A value is 1, B value is 0. So equivalent decimal number is 2. In fact, the reason why we are having the cell numbers are differ, locationally we are having the same place, but cell numbers are differ. And basically, ultimately, what we are understanding is how we are accommodating variables based on this, the cell numbers what we are talking will differ. How we are accommodating variables based on this, we'll be looking at the difference. So, based on how we are accommodating variables, the cell numbers will differ. If you work out like this, here we are having A is MSB, so 0, 1, 2, 3. Whereas here A is LSB, 0, 1, 2, 3. A is here row heading, so horizontally we are writing. A is here column heading, so that we are writing here column wise. That way you can understand, you can remember. Of course, as a two variable function, there is no scope to discuss anything much. Let us try for 3 variable, 4 variable K-maps. From there, we can look few other points. Let us come to a 3 variable Boolean function. Consider the Boolean function f and the variables x, y, z. For this 3 variable Boolean function, we are having possibility of many different K-map formats. And here I mentioned few of the possible K-map formats. The formats, how they are differ, if you see, the formats are differ based on how we are accommodating variables as row and column headings. Based on that, we are having the K-map formats will differ. For example, in this format, I am having xy as the column heading and z is the row heading. Whereas here, x is a row heading, y and z are column headings. Coming to this, here I took xy as a row heading, z is a column heading. Here x is a column heading, y, z row heading. Suppose if at all we are looking to the cell number here, the cell number for this, if you look well, the cell number we are reading here as 6. Similarly, in this format, let us refer to same location. In this format, let us refer to the same location. Here, if you look to the cell number we are reading here as 3. How it is so? How it is so? If it is a question, we are looking here, xy values 1, 1 and z value is 0. So we know equivalent decimal value is 6. Coming to this, we are having here x is 0, y and z, if you read, y and z are 1, 1. So because of xyz values 0, 1, 1, the cell number will be 3. So I already said the cell numbers what we are looking, they are differ based on how we are accommodating variables. Based on this, the cell numbers will differ. Like this, we need to read the cell numbers for each one of the cell. So try yourself. So maybe you need to note it in your notes. So try yourself the cell numbers for these two formats. So if you try well, the cell numbers what we are reading are in this format. If you read xy are column headings, x is MSB column heading. So some time back I was talking the two variable. So MSB's column means column wise. Let's start. It is 0, it is 1, this is 2, this is 3, it is 4, it is 5, this is 6 and this is 7 if you try well. So be clear. After writing 0, 1, here we are having 1, 1. We are not having here 1, 0. We are having here 1, 1. Why it is 1, 1? I will talk later. We will talk little later why it's supposed to be. So, but be clear. It is not 1, 0. Here, even here also it is not 1, 0. It is 1, 1. Similarly, coming to this. Here x is row heading. So, the cell numbers we are writing row wise. So, left to right. Column wise means bottom to top to bottom. So, row wise here we are having 0, 1, 2, 3, 4, 5, 6 and 7. Similarly, let us look here other two formats what I mentioned on the board. In this format, x, y are row heading, z is the column heading. So, based on this, the cell numbers we are supposed to write the row wise. And if you try well, say for example, here if you try the cell number we are reading here, it is 3, x, y, z, 0, 1, 1, 0, 1, 1 is giving 3. If at all we are looking to this, here the cell numbers we are having x, y, z. If you look, based on these cell numbers, we must write as a 5 because 1, 0, 1, 1, 0, 1 is giving 5. So if you look like this, here the cell numbers are 0, 1, 2, 3, 4, 5, 6 and 7. Coming to this here 0, 1, 2, 3, 4, 5, 6 and 7. So here also in this 3 variable K-maps, the variables what I use in the 2 variable case, the similar work possible to use here also. So you can see here, say for example, if you look to this, X must be here uncomplementary form because X is 1. And here for right side 2 columns, Y value is 1. So Y must be uncomplementary form. Y must be uncomplementary form. And middle 2 columns, Z is 1. So Z must be uncomplementary form. So without writing anything here, it is default. We need to accept X complement here. Without writing anything, we need to accept looking to this as a Y bar. Similarly, for the first column and last column, it must be Z complement. So as I said, wherever possible, work out with the minimum writing work. It is always good. Without writing Z complement or Y complement or X complement, which is possible to understand with this minimum rating what we are having here. So like this, you can extend for any other format what we are looking at the board. You can try. So if you look here, hopefully you are working yourself. X, Y, Z. Keep attention well. By chance any mistake is happening, you rectify yourself while noting X, Y, Z. Coming to this here, it is X, Y, Z. In few books, you may be looking by few authors, little more detailed way. X complement, Y complement, X complement, Y. It is X, Y. This is X, Y bar. Like this in a detailed way, sometimes we'll be looking. All that work is okay, but I'm telling, wherever possible, you need to cut down the time as far as the objective type question papers are concerned. Whether you are writing in detail or you are writing the minimum thing what I written with the red color, the usage purpose, it is enough. It is enough. So don't look with all these details. That is my suggestion. But if at all you are having already this sort of practice earlier, if I am insisting you to switch immediately, it may be a little difficult for you. But with the practice, try to overcome that. Try to work out with the minimum writing work. It is always good. Okay. Let's come to now the 4 variable function. Let us take an example of 4 variable function f of a, b, c, d. So based on this, a is MSB variable and so on, d is LSB. Here also we are having 2 possible K-map formats. We are having in this format A, B are the row headings, C and D are the column headings, whereas in this format we are looking A, B are the column headings and C, D are the row headings. Based on our work on the 3 variable, we need to work little fast with the 4 variable K-map. While having AB as the row heading on 2 variables, we are having as usual 4 possible combinations. So each possible combination is coming to be 1 row heading. So 0, 0, 0, 1, 1, 1, 1, 0. Be clear, it is not 1, 0. It is 1, 1, later 1, 0, similar to the 3 variable. So in the 3 variable, we are having either maybe column headings or maybe row headings with 2 variables. Other one default is single. But here, both column and row headings are 2 variables. Because of this, we are having 4 rows, 4 columns. So anyway, we come to CD. On CD, we are having 4 possible values. Each possible value is 1 column heading. As usual, 0, 0, 0, 1, not 1, 0. It is not 1, 0. It is 1, 1, later 1, 0. And coming to this, here AB are the column headings and CD are the row headings. AB values we are looking as so and so. CD we are having as so and so. Now let us look here also as similar to our earlier discussion. Let us try to recognize just one or two samples, the cell numbers. Later we'll try to write the cell numbers for every cell. If you look here, the cell number, with all the discussion what we learned, the 2 variable, 3 variable, definitely you supposed to write here the cell number as equal to 3. And location wise, at the same place in this format, if you look, you must write the cell number as 12. So how we are writing, if you check, for this case, we are having AB value 0, 0 for this row, AB is 0, 0. And CD we are having as 1, 1, which is giving a decimal value as 3. Coming to this, here AB we are having as 1, 1. And CD for this row 0, 0. Hence, we are looking here, the equivalent decimal number for 1100 is 3. Sorry, 1100 is 12. So that the cell number is 12. So like this, we are having possibility to write the cell numbers for each one of the cell. So take some time and write the cell numbers in your notebook properly for both these formats. So by this time you might be completed writing the cell numbers. AB are row headings. I was talking with 3 variable, 2 variable also. So once AB are row headings, A is MSB, so row wise you have to write the cell numbers. So this is coming 0, 1, 2, 3, if you try well, 4, 5, 6, 7, 8, 9, 10, 11 and so on. This is 15. Similarly, in this format, AB are column headings, so that column wise 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and so on. This is 15. Okay. Before going to use these K-maps, I have to look few more points from this K-maps. Suppose we are writing the product form, say for example for this 2. The product form for this cell 2, if you write, the product form we are reading as AB complement. Similarly, if you write the product form for this cell 3, the cell 3 product is AB. Whether we are reading these products from this format or from this format, these are the products only. For cell 2, A, B complement. Maybe looking to these headings or maybe looking to these binary values. Similarly, for cell 3, A, B. If we compare the cell 3 product with cell 2 product, the cell 3 and cell 2 products are common in variable A, but they are differ in variable B. They are differ in variable B. If you look like this, in these K-maps, if you look like this, if you are having any 2 cell products which are differ, in general I am talking, may not be limiting to only 2 variable. In general, maybe of 3, 4 or any number of variables, if you speak, if any 2 cell products are differ in only one variable, any 2 cell products are differ in only one variable, such 2 cells must be named as adjacent cells. If any 2 cell products are differ in only one variable, such 2 cell must be named as adjacent cells. So better note down the definition of adjacent cells. Note down. If any two cell products are differ in only one variable, if any two cell products are differ in only one variable, such two cells are said to be adjacent cells. Such two cells are said to be adjacent cells. So, based on this two variable case, we are looking the adjacent cells for this cell 2. For this cell 2, we are having the adjacent cell, it is cell 3. And similarly, if you write the product form for cell 0, if you write the product, for cell 0, the product we are having as A complement, B complement. These two cell products, if you compare, they also common in variable B but differ in variable A. They also differ in only one variable. Based on this, cell 0 also an adjacent cell to cell 2. And we are looking further. Cell 0 is an adjacent cell to the cell 2 while differ in variable A, whereas cell 3 is an adjacent cell to the cell 2 while differ in variable B. Whether we are doing this sort of work with this format or with this format, the results are same. Even if you look here, for cell 2, the product is A-B complement. For cell 3, the product is AB. These two cell products are differ in only one variable B. Similarly, for for cell 0, the product is A complement, B complement. So they are differ in only one variable, that is in A. So the format may be of anything, the results must be same. Like this, if you look in this two variable K-map, for every cell we are looking exactly, there are two cells which will be adjacent cells. In this two variable K-map, we will be looking for every cell exactly, there are two cells which will be the adjacent cells. Of course, as a two variable K-map, there is not any much scope to speak. Let us go for 3 and 4 variable K-maps, then there we can speak little more details. I said in the two variable K-map, if you look like this, every cell will be having only two cells are adjacent cells. And before going to the 3 variable, if at all you are having a question, you have to look. The question is, here for cell 2, 0 and 3 are adjacent cells, 0 and 3. Why not this one? If you take as a question, if you write one product, the cell 1 product we are having as A complement B. When the cell 1 product is A complement B, we are looking with reference to this cell 2, we are talking 2 is a reference cell. They are different in A as well as in B. Hence, we are speaking these two cells are not adjacent cells. So, whether we are reading from this or from the same story, cell 1 product, if you read, it is A complement B. So, these two cells are not coming as the adjacent cells. It is the reason why I said in this two variable K-map, for every cell, for any reference cell, we are having exactly two cells are adjacent cells. Only two cells will be having as adjacent cells. For understanding, I did all this work to explain, but in a simple way, you can have an observation here without any such thing. We are interested to know what are the adjacent cells, say for example, for cell 2. The work what we are doing is just we are looking which are the cells which are having common line in the cell 2. The cell 3 is having a common line. Cell 0 is having a common line. Based on this cell 3, cell 0 must be adjacent cells. And further we can speak cell 3 and 2 are different B. Cell 0 and 2 are different A. Further we can speak like this. Whether we are looking to this format or this format, same thing. For cell 2, we are having common line 3 and 0. So that we are having these 3 and 0 are adjacent cells with so and so, different so and so variables. differ in so and so variables. So on the whole, if you look like this, for every cell exactly we are having only 2 cells or adjacent cells in this 2 variable K map. Let us come to this 3 variable. Let us try to look what are the adjacent cells, say for example for cell 3. For cell 3, if you look to the adjacent cells, common lines we are having 1, 2, 7. So we supposed to speak now. This 1, 2 and 7 must be adjacent cells. And if you look with respect to which variable, cell 1 is adjacent to 3 and so other cells if you speak. Cell 1 is adjacent cell to the cell 3 while differ in variable y. While differ in variable y. We are looking 1, 3 are common with respect to variable x and z, but they are differ in variable y. Similarly, 2 and 3 if you check, they are common with x, common with y, but differ in variable z. 7 if you check, they are common with y and z, but differ in x. Whether we are referring to this or any other format, the same result, same thing we'll be having. Even if you look from this format, this 1, 2, 7, 1 is while different variable y, 2 is while different variable z, 7 is while different variable x. Even if you check from this or this, same result. As long as our reference cell is 3, 1, 2, 7 are 1, 2, 7 are adjacent cells while differ in so and so variables. Okay. Now if you write any other cell product and if you check the cell 3 product, any other cell product will be differ in cell 3 product in more than one variable. If you write now with any other cell product and if you check the cell 3 product, any other cell product is different cell 3 product in more than one variable, So if you look with any other cell product, we are not reading any other cell as an adjacent cell to the cell 3. As long as our reference cell is 3, these are the only 3 cells which will be reading as an adjacent cells. So like this, if we check in this 3 variable K map, we are looking for every cell exactly there are 3 cells which will be adjacent cells. For every cell we'll be looking exactly there are 3 cells which will be adjacent cells. So suppose if you check for cell 6, cell 6 is concerned, common lines we are looking 2, 4, 7, they are the adjacent cells. And 2 is differ in variable x, 4 is differ in variable y, 7 is differ in variable z. It is observation, you can see. For cell 6, it's a reference cell we are talking. 2, 4 and 7 are adjacent cell. 2 is while differ in variable x, 4 is while differ in variable y, 7 is while differ in variable z. Whether we read from any other format, it must be same. Even if you look here from this, we are looking 2, 4, 7 are adjacent cells, 2 different x, 4 different y, 7 different z. Even if you look from here also same. The reference cell is 6. The common line we are having the 2, 7. Common line we are having with the 2, 7. If you fold horizontally, this line will be the overlap with this line. When this line is overlapping with this line, we are looking between the cell 6 and 4, there is a common line. Between the cell 6 and 4, there is a common line. So that cell 4 is coming to be an adjacent cell. Even if you look here, the reference cell is 6. The common line directly we are looking 2, 7, 2, 7. And if you fold this K map vertically, this line will be overlap. Whenever these 2 lines are overlap, between the cell 6 and 4 there is a common line. So that cell 4 is coming to be an adjacent cell. And also you can see further, they are differ in variable y and of course other 2 variables so and so. So if you look like this, in this 3 variable K map, for every cell we are having exactly there are 3 cells which are adjacent cells. when we are referring to any reference cell, which may be the rightmost place or leftmost place, or in this format maybe first column in the last column, in these formats. For that purpose, we need to fold. For these two formats, we have to fold vertically, then we will be having a common line. For this, we need to fold the maps horizontally, then you will be looking for corner cells, the common line. Just for observation, I'm speaking, just for clarity, I mentioned all these things. So with a simple observation, we are able to speak this. Anyway, finally, in this 3 variable K-map, for every cell we are reading exactly, there are 3 cells which will be adjacent cells. Now let us come to 4 variable K-map. In this 4 variable K-map, based on the knowledge on the 2 variable, 3 variable, definitely we need to speak. For every cell, we supposed to read exactly 4 cells are to be adjacent cells. For every cell exactly, we supposed to read the 4 cells are to be adjacent cells. Say for example, we are interested to look what are the adjacent cells, say for cell 3. For cell 3 adjacent cells, if you read, common lines you have to look. For cell 3 common line we are having with 1, 2, 7 directly, we are speaking 1, 2 and 7 directly we are able to speak with a direct observation. And if you fold the map vertically, this line will be overlap. Whenever these lines are overlap, 11 is coming to be adjacent cell to cell 3 because it is a common line. Hence, cell 11 is coming to be an adjacent cell. And if you check each one of these cells with reference to this cell 3, with respect to which variable they are adjacent cells. One is adjacent cell, we can look while different variable C. While looking to the binary format, if you speak, we are talking while different variable C. So the binary format, as I said, you can use this sort of notation in every K-map format. So if you use the same sort of notation here, so we are looking here, this is it is A, it is B, this is C, this is D. Coming to this, A, B, C, D. So what I said, cell 1 and cell 3 we are comparing. So instead of looking to the binary, we can use this, we can observe from this. So they are different variable C. Similarly, 2 if you check, they are common with A, sorry, they are common with A and they are common with B, they are common with C, but differ in variable D. Differ in variable D. So similar work if we do, 7 is differ in variable B. So what I given C, this is, sorry, said D now. Okay. And if you look 11, B, C, D are completed. Definitely it's supposed to be different with respect to other variable other than this B, C, D. Other than B, C, D, the leftover variable is A. It must be different variable A. And if you observe, it is the answer you will be having. So 11 and 3 we are comparing. They are common with B, they are common with C, common with D, but differ in variable A. Differ in variable A. So what is observation? With respect to one variable, you will be having only one cell as an adjacent cell to the reference cell. With respect to any particular variable, only one cell will be reading as an adjacent cell. So function is on 4 variables. For this reference cell, what are the cells we mentioned as adjacent cells? Each cell is adjacent cell with respect to one particular variable. Now, if you write the product form any other cell other than this, and if you try the cell 3 product any other cell is not resulting as an adjacent cell to the cell 3. Only these are the 4 cells which will be resulting as an adjacent cells to the cell 3. Whether we read from this or from this, the answers are same. Our answers on the adjacent cells will be same. For cell 3, the adjacent cells will be 1, 2, 7 and 11. Here we are folding vertically. Then this 3 and 11 with the common line, so 11 is adjacent cell. And if you look further, 2 is adjacent cell because of different D. 1 is adjacent cell while different variable C, and so and so. So format may be of anything, ultimately the results are not changing. Irrespective of the K-map format, the results must be same. Based on the format we are reading different results means we are doing something wrong. We are unable to use a map properly, then only based on the formats we will be having some different results. Format may be of anything, ultimately the results must be same. So based on this we are speaking now, in this 4 variable K-map, for every cell exactly we are having, there are 4 cells which will be adjacent cells, Now with all this knowledge we are speaking now, if we take for a function of n variables, if I is a reference cell, then if I am putting a question, how many number of cells are adjacent cells? Definitely your answer is coming as n number of cells. So it is the work what we are having with the 2, 3, 4, from that we are speaking. The 2 variable K-map, for every cell exactly 2 cells are adjacent cells. The 3 variable K-map, for every cell exactly 3 cells are adjacent cells. In the 4 variable K-map, exactly for every cell we are having 4 adjacent cells. With all this knowledge, we are talking a general way. Whenever we are having a function on n Boolean variables, whenever the function is on n Boolean variables, if I am talking a cell I as a reference cell, then if you take the question, how many number of cells are adjacent cells? The answer to this is n number of cells must be adjacent cells. For any reference cell, we are looking like this, J, K like this, n number of cells, total n number of cells are adjacent cells. Total n number of cells are adjacent cells. And also further you can speak with all this knowledge. If cell J is different variable I in the cell J is different in cell I product in variable X. Suppose cell J is differ in variable X comparing the cell I product. Basically what I am talking is cell I, cell J products are differ in variable X when we are rating the product. Now the remaining cells, if we look, definitely the remaining cells will be n-1 number of cells. n-1 number of cells. If you look to the remaining cells, we are not reading any other cell as an adjacent cell to the cell I because of the same variable X. We are not reading any other cell as an adjacent cell to the cell I because of the same variable X. Any other cell will be reading as an adjacent cell to the cell I other than the variable X. It is observation what we are having. While talking this, I already said, if we are looking here, cell 1 is an adjacent cell to the cell 3 while different variable C. Cell 1 is an adjacent cell to the cell 3 while different variable C. The remaining cells, if we look, we are not reading any other cell as an adjacent cell to the cell 3 other than the because of same variable C. Any other cell is an adjacent cell to the cell 3 other than the variable C. Because same variable C, we are not reading any other cell as an adjacent cell to the cell 3. So, whether we are referring to 3 or any other cell, it is same story in the 4 variables and so with the 3 as well as the 2 variable. So, on the whole, the final conclusion on this K-map, the basic work is, for any reference cell, we are having exactly n number of cells are to be adjacent cells. And we are looking, if cell J is an adjacent cell to cell I while different variable X, from the remaining cells if we look, we are not reading any other cell as an adjacent cell to the cell I because of the same variable x. Any other cell is an adjacent cell to the cell I other than the variable x. These are the observations what we are having for the basic work of this K-map. Now, with all this knowledge, we are in a position to use the K-maps for reading the minimal expressions. So again, let us start the usage of K-map with a small example of the two variable function. So consider a two variable Boolean function with minterms 0 to 3. Minterms 0 to 3. So when we are having the function with the minterms of 0 to 3, for this function conventionally, if you try to read the minimal form, then definitely we are reading first expanded canonical SOP form. This is the expanded canonical SOP form. After reading expanded canonical SOP form, our work is for simplification. For that purpose, we are grouping the terms. So we are having possibility to group these products. It is giving using properties B bar. Similarly, we are having possibility to group the last two. It is giving A. It is giving A. So all the basic things we learned. So don't expect again to repeat. We are looking here A complement, B complement or with AB complement. So basically we are looking B complement is a common. So A complement or with A from the first two terms. It is 1, so that B complement similarly there. And also we are looking, don't get confused. This term we are using to group this as well as this. With one example in the very beginning of the class, with one example, first exam, maybe in the first few pages we will be looking to the example. We took this similar type of thing. The product can be used at more than one place based on first property we said. Anyway, hopefully you are remembering. It's not a problem. If still any problem, rewind the video, go to the beginning class, or hopefully you are making a notes, look to your notes, look to the first property, and there later the first property, some question is there, you can check there how we are giving this. So finally, we are having here the expression is A or with B complement. Now using properties, without all this sort of work, directly from the K-map we must read. Directly from the K-map we must read this simplified expression. Okay. We said the K-map is an alternative way of writing truth table. What is the work we are having the truth table? The similar work we need to do even here also. If we develop the truth table for this function, when we are developing the truth table for this function, it is very well known for us, corresponding to the rows 0 to 3, corresponding to the decimal number rows 0 to 3, or corresponding to the combinations decimal 0, 2 and 3, we are writing the function output is 1. We are writing the function output is 1 in the K-map. The K-map is alternate. We are writing function output is 1 in the truth table, not in the K-map, sorry. Whenever we are developing a truth table for this function corresponding to the decimal 0, 2, 3 rows, we are writing the function output is 1 in the truth table. So K-map we said it is an alternative way of writing truth table, so that similar work we will be having here. So instead of row we are using here word as cell. So in the corresponding cells we supposed to write the function output is 1. Hence in the cell 0, 2 and 3, the cells 0, 2 and 3, we must write the function output is 1. We must write the function output is 1. And wherever we are not writing anything, default means it's a max term. Default means it must be a maximum. Function output is 0. Say for example, here we are not writing anything. The indication is a maximum with a function output of 0. Maybe here or here format, not the matter. Corresponding cell 1 is function output is 0. The latter here, conventionally the work was grouping of the min terms. Using K-map terminology, we must speak now the grouping of the cells. Based on the K-map terminology, we need to speak now the grouping of the cells. Grouping of the cells is possible. Grouping of the cells is possible either maybe 2 cells or maybe 4 cells or maybe 8 cells, or in general the group of to the power of m cells where m is positive integer, where m is positive integer. So grouping of the cells possible only with this rule. Maybe 2 cells, 4 cells, 8 cells, etc. The group of 2 to the power of m cells is called subcube. Group of 2 to the power of m cells is called subcube. So subcube will be either maybe 2 cells or maybe 4 cells or maybe 8 cells, or in general with this format. 2 cell subcube is pair, 4 cell subcube is quad, 8 cell subcube is octal. So we are not having the subcubes with 3 cells, 5 cells, 7 cells, 12 cells, like this we are not having subcubes. Subcubes will be only with this format. The example what we are talking here, the 2 variable example what we are looking here, in this 2 variable example, in this 2 variable function, we are having here possibility of the 2 cell subcubes. We are looking to the possibility of the 2 cell subcubes. In general, it is possible to group the 2 cells if and only those 2 cells are adjacent to each other. It is possible to group the 2 cells if and only those 2 cells are adjacent to each other. If you look here, for the cell 0, the cell 2 is an adjacent cell. So it is possible to group these 2 cells. And one point you need to be clear, after entering the values in the K-map, if you use the word cell or adjacent cell, if you use the word cell or adjacent cell, default all these words are referring to only those cells which are with the function output of 1. We are referring to only the cells which are entered the value of 1. Once we are writing the values in the K-map, so once we develop the K-map corresponding to one particular function, as and when we are using the word cell or adjacent cell, we are referring to only those cells which are with the function output of 1. So we are not at all referring to this. Based on this, we are not referring to this cell 1. So anyway, come to this. For cell 0, the adjacent cell is cell 2. So that 0, 2 is one possible subcube of 2 cells. And coming to this cell 3 not possible with the group to group with the 0. The reason is they are not adjacent cells. That differ in variable B as well as A. I am talking now after grouping these 0, 2, when I am talking about 3, I said not possible to group with the 0. The reason is they are different in A as well as in B. But of course, it is possible to group the cell 3 with the cell 2 because they are adjacent cells. They are adjacent cells. 2, 3, 1, other 2 cell subcube. Whether we are reading from this or we are reading from this, it is one and same. One group is 0, 2. Other subcube is this 2, 3. So like this, we are go on marking the subcubes until to cover all the cells which are with the function output of 1. Like this, we are go on marking the subcubes like this until to cover all the cells which are with a function output of 1. So we are looking with these two cells, with these two subcubes, we are having coverage of all the cells. Then as for the marking of the subcubes are concerned on this function, it is a terminal step. The latter work is coming to be reading the product form for each one of the subcube. To read the product form for each one of the subcube, the rule what we are having is, better note down. For reading the product, the rule what we are having is, better note down. In general, let me talk, not limiting to two variable case. In general, let me talk. So, note down. The variables which are common for the total subcube, only those variables are present. The variables which are common for the total subcube, only those variables will present. Only those variables will present in the product representation of the subcube. Only those variables will present in the product representation of the subcube. So, while noting this statement, default is we are having a means the variables which are not common for the total subcube, those variables are not present in the product representation. No need to waste time. Default is indication the variables which are not common for the total subcube, those variables are not present in the product representation. The variables which are common for the total subcube, only those variables will present in the product representation of that subcube. So, if you look based on this statement, for 0, 2, we are looking the variable A is changing, it won't present in the product representation, whereas the variable B is common, hence the variable B is present in the product representation. So, this is B complement. And similarly for 2, 3, if you look, the B variable is changing, it won't present, but A is not changing, it must present. Whether we read from this or from this, same result. For 0, 2, product is B complement. Even if you look here, same thing, it's a B complement. Similarly for 2, 3, it was A, here also it is A. So, format may be of anything, the results must be same. After reading these products, we are taking R operation among these products. If you take R operation among these products, of course, expression is A or B complement. It's the one what we mentioned conventionally. When from the conventional work, if you look, it was the same thing. From the conventional work, if you see here, this is basically a product 0, it is 2, this is 3. The grouping was for 0, 2, it was giving B complement. The grouping was for 2, 3, it was giving A. So, ultimately I said, the formats may be of anything, even with the conventional work, if we compare, the results must be same. If we are having a different results, means we are doing something wrong. Okay, as a 2 variable example, a small thing it is. Let us go to now 3 variable, later let us go to 4 variable function. So, note down. Find the minimal SOP expression. Find the minimal SOP expression for the function f of xyz. For the function f of xyz. Zero, 1, 3, 5, 6, 7. 0, 1, 3, 5, 6, 7. So, just take some time and try. So, when you are trying, as per your convenient, whatever the practice you are having earlier, you can use any one of the format. No need to try with all the 4 formats. It is a wasting of the time. When you are trying yourself, you need to use any one of the format. For a cross check, you can see from the work what I am doing on the board. But yourself, no need to work out with every format, not at all required. You may be having familiarity maybe with this, use this. You are having familiarity with this, use this. Or what is the format, or what is the format you are having familiarity earlier, better to use that. So this, of course, 3 variable function, we know. So you might try it with one of the format. Let me discuss now. So in the corresponding cells, we must write the function output is 1, 0, 1, 3, 0, 1, 3, 5, 6, 7. 0, 1, 3, 5, 6, 7. 0, 1, 3, 5, 6, 7. Any format is not the issue. 0, 1, 3, 5, 6, 7. Zero, 1, 3, 5, 6, 7. Okay. After entering these values, listen well. Let me discuss few important points. Listen well. When we are marking, when we are trying to identify the subcubes, we need to start the identification of subcubes with this step. Note down. First step, identify all independent cells. Note down. First step, identify all independent cells. Identify all independent cells. If we look to this example, the 3 variable function what we are talking, suppose in this example, consider cell 7 is a max term. Consider 7 is max term. 7 is not a min term. So if it is not a min term, it must be max term. Consider cell 7 is a max term. If cell 7 is a max term, just look the status of the cell 6. If you look to the status of the cell 6, your answer is supposed to be, it is an independent cell. Your answer is supposed to be, it is an independent cell. Cell 6, if you look here, if any cell is adjacent to cell 6 means it must be either 2, 4 or 7. But it happens so all these are max terms. Whether we are reading from this format or from any other format, it's the same thing. Cell 6, if you look, 2, 7, 4, all these are max terms, so that it is independent. So whether we read from this, or from this, or from this, it is an independent cell. But come to this cell 5, we are not talking it's an independent cell. For cell 5, we are having an adjacent cell is 1. Is it? You can see from here directly, in fact. But if at all you are looking to this, in this format, direct observation. But here, if at all you are looking, don't say it is independent. It is there, one adjacent cell, 1. When from here, directly observation. But if you look here, don't say it is independent. You are having here from here. Folding, you are getting. Anyway. So, if any such independent cell or cells we are having, those independent cells we need to identify first. Of course, the example what we considered here, in this example, we are not having independent cells. For every cell we are having, there is one cell as an adjacent cell. In this example, what we are looking, for every cell we are looking, there is one cell as an adjacent cell. But here we are discussing more generic procedure. We are looking here. First, we are trying to recognize the independent cells. So we are not having any independent cells. Later, the next point, note down. Mark all possible two-cell subtubes. Mark all possible two-cell subtubes. Mark all possible two-cell subtubes such that they should not be part of any larger size subtube. Mark all possible two-cell subtubes such that they should not be part of any larger size subtube. So what we are talking is mark all possible two-cell subtubes such that they should not be part of any larger size subtubes. So based on this, the meaning is whenever we are marking two-cell subtube, we need to take care it should not come as a part of 4-cell or 8-cell or in general in any larger size subtube. So by using this rule, by using this condition, we are supposed to mark the subtubes. Why this condition is required? If you are having a knowledge, you are having clear understanding on the word of the prime implicant, you could have been identified why we need to follow this condition here. But till now in the class, we not discuss the meaning of the prime implicant, but just I'm quoting. Somebody is having already learning, somebody already having familiarity in this wording, maybe from the college or maybe some other source. Definitely, with the knowledge of the prime implicant, it is possible to speak why this condition is this condition we need to follow. Anyway, we'll discuss the due course, the word prime implicant. But at this point, at this junction, just accept as a condition. The condition what we are talking is, whenever we are marking the two-cell subtube, we need to take care that subtube should not come as a part of any larger size subtube. This two-cell subtube should not come as a part of the larger size subtube. That condition we need to follow to mark the two-cell subtube. So based on this, let's come to this function, the example what we are looking as a 3-variable function. So in this 3-variable function, if you look here, they are having this 0, 1, 1, 2-cell subtube. It is not coming as a part of any larger size subtube. So 0, 1, 1, 2-cell subtube. It is not coming as a part of any larger size subtube. And also we are looking this 6, 7 is other 2-cell subtube. It is not coming as a part of any larger size subtube. But definitely we are not taking this 1, 3 or 3, 7 or 5, 7 as a 2-cell subtubes. Because 1, 3 or 3, 7, 5, 7 or 1, 5 all are coming to be the part of the larger size subtube. Based on that condition is not allowed. So the subtube what we are marking 2-cell, वो subtube दूसरा subtube में part नहीं होना चाहिए. So whether we are reading from this or any other format, our results are same. 0, 3, 6, 7. 0, 1, 6, 7. 0, 1, 6, 7. 0, 1, 6, 7. Format may be of anything, the results must be same. So no more 2-cell subtubes, no more 2-cell subtubes. Later, next one. So note down. Mark all possible 4-cell subtubes. Mark all possible 4-cell subtubes such that they should not come as a part of any larger size subtube. Mark all possible 4-cell subtubes such that they should not come as a part of any larger size subtube. Mark all possible 4-cell subtubes such that they should not come as a part of any larger size subtube. So the meaning is, whenever we are marking a 4-cell subtube, it should not come as a part of a subtube of 8-cell or 16-cell and so on in general in any larger size subtube. So talking every time like this, Let us speak more generically. Whenever we are marking a subcube of to the power of m cells, we must follow a condition. This subcube should not come as a part of the subcube of to the power of m plus 1 to the power of m plus 2 and so on. Whenever we are marking a subcube of to the power of m cells, we need to take care it should not come as a part of the subcube of to the power of m plus 1 to the power of m plus 2 and so on. So this is a rule we need to follow in general to mark the subcube. Function may be with any number of variables. Function may be with any number of variables. By using this rule, we need to mark the subcubes. Let us come to our example of 3 variable function. In this 3 variable function, we are having possibility for 1 4-cell subcube. In this 3 variable function, what we are looking, we are having possibility for 1 4-cell subcube. The 4-cell subcube we can see here as this 1, 3, 5, 7. This 1, 3, 5 and 7. So you can see whether we are referring to the first format or any other format, it is the same thing. 1, 3, 5, 7. 1, 3, 5, 7. 1, 3, 5, 7. Format may be of anything. It is only 1 4-cell subcube. As I said already while discussing the 2 variable example, like this we are go on marking until to cover all the cells which are with the function output of 1. So with this 4-cell subcube we are having coverage of all the cells which are with the function output of 1. Hence, as for the marking of the subcubes are concerned, it is a terminal step. As far as the marking of the subcube is concerned, subcubes are concerned, it is a terminal step. Later, for each one of the subcube, we need to read the product form. So how to read the product forms? We already know. What are the variables which are common on the total subcube? Only those variables will present in the product form. The variables which are not common on the total subcube, those variables are not present in the product representation. So based on this, look into any format. If you look for this 0, 1, for this 0, 1, the product is x complement, y complement. From any format, you can see for the 0, 1, the product is x complement, y complement. You can use, as I said, maybe binary notation or maybe variable notation as per your convenience. Suppose if you look here, I am having here x complement, here y complement. So I am looking x complement, y complement. Or if at all you look to the binary variable notation, x is 0 common, y is 0 common, z is 1 not common, so z is not present because 0, 0 we are talking x complement, y complement and so on. If you read like this, the 6, 7 is xy and 1, 3, 5, 7 is z. From any format if you look, it is these are the products we are having. Now we are taking OR operation among all these products. While taking OR operation among all these products, the expression is x complement, y complement, or with xy, or with z. So it is the minimal SOP expression for the function f of xyz. It is the minimal SOP expression for the function f of xyz. X complement, y complement, or with xy, or with z. Now, let us try for a 4 variable function. Let us try for 4 variable function. Let us take a function of 4 variables. Note down. Find the minimal SOP expression. Find the minimal SOP expression for the function f of ABCD. For the function f of ABCD. where f of ABCD is where f of ABCD is 2, 4, 5, 7, 11, 13, 15. 2, 4, 5, 7, 11, 13, 15. Develop the K-map for this. Use any one of the format. We already observed format is not the issue. Format may be of anything. Ultimately, on the given function, the results are same, irrespective of the number of variables in the given function. So develop the K-map for this function. Any format as per your convenience, your familiarity, you can use. So if you look here, the main terms we are having as 2, 4, 5, 2, 4, 5, 7, 11, 13, 15. Two, 4, 5, 11, 2, 4, 5, 7, 11, 13 and 15. 2, 4, 5, 7, 11, 13 and 15. Now, what we noted, we need to identify first independent cells. Look to the status of cell 2. Look to the status of the cell 2. The cell 2 is an independent cell. The cell 2, we are recognizing which it is an independent cell. Any cell is adjacent to cell 2 means it must be either 3 or 6 or 0 or 10. But it happens so, this 0, 3, 6 and 10 all are max terms. All these are the max terms. Whether we are reading from this or from this, same thing. This cell 3, 6, 0 and 10, all these are max terms. So that the cell 2 is an independent cell. Are you having any more independent cells? Of course, answer is no, no more independent cells. For remaining cells, for every cell we are looking, there is an adjacent cell. So only cell 2 is an independent cell. Later we are coming to the second step. Look to the notes well. The second step, what we said, we need to mark all possible 2-cell subcubes with a condition. Condition is, what are the 2-cell subcubes we are marking? It should not come as a part of any larger size subcube. It should not come as a part of any bigger size subcube. So if you look to the 2-cell subcube, we are having this 4, 5, 1 2-cell subcube. This 11, 15 is another 2-cell subcube. 4, 5, 1 2-cell subcube. And this 11, 15 is another 2-cell subcube. Whether we are reading from this or from this, the same thing. One is 4, 5, other is 11, 15. But definitely we are not marking 5, 13 or 5, 7 or 13, 15 or 7, 15 as 2-cell subcubes. Because what the 2-cell subcubes we want to mark, it should not come as a part of any larger size subcube. If you mark what we said 5, 13 or 7, 15 so and so, they are coming to be the part of the larger size subcube that is not allowed. So no more 2-cell subcubes. Then we are trying to read the 4-cell subcubes. The rule is, what are the 4-cell subcubes we are marking? It should not come as a part of any larger size subcube. If you look here, we are looking, there is one 4-cell subcube. That is the group of this 5, 7, 13, 15. That we are using this format or this format, we are having this is this 5, 7, 13, 15. 5, 7, 13 and 15. So with this 4 cell subcube, we are having coverage all the cells. Coverage of all the cells means cells we are referring to only the cells which are in the functional output of 1. We already mentioned that. So we are having coverage of all the cells. Hence, the marking of the subcubes are concerned, it is a terminal step. The latter work is coming to be reading the product form. Reading the product form. You try yourself. Try yourself.